Welcome back, AP Stat, to the second and final part of Chapter 26. We're going to review the assumptions and conditions to perform inference about the coefficients of the ideal regression line. If you remember from last time, the ideal regression line is mu sub y is equal to beta naught plus beta 1 times x. Okay? So we're going to be doing regression specifically on beta 1, the slope of the ideal regression line. So you need a scatter plot to follow a linear pattern in order to do inference on beta 1. Okay, so in order to do inference with a regression line, you need to have a linear pattern in the first place. And the textbook calls this the straight enough line condition or straight enough condition. The scatter plot looks generally like a straight line, that is, it is not curved. The independence assumption, all right? To check for independence, we need to check for randomization and for random residuals, all right? So we need data collected from a random sample or randomized experiment, and we need the residuals to look random too. The residuals cannot follow a pattern like we see at the bottom right of our screen. We also need to assume equal variance, that is the variability, whether we measure variance or standard deviation of y, should be the same for all values of x, all right? And I explained last time that one way of understanding that is, let's say could we put guardrails on either side, straight line guardrails, and the data would kind of stay within those guardrails. That's what equal variance looks like. The variance stays the same. Means the spread of the points relative to the regression line remains consistent. Perfectly consistent? Nah, that's impossible. Just consistent enough that it doesn't raise an eyebrow. And the book has this humorously named "Does the plot thicken" condition to check that. And we can analyze the residuals for a fan pattern like the one at the bottom right, right? If the variance, if the variation of the y values is not the same for all of the x values, you're going to get a fan pattern like we see at the bottom right when graphing the residuals. And there's one more condition. The normal population assumption, we need to ensure not only that the distribution of the residuals for the ideal regression line must be consistent, but they must be nearly normally distributed, all right? So just like those residuals we see in the histogram from our textbook, that's what the residuals need to look like. So we see the nearly normal condition, distribution of the residuals is unimodal and symmetric. And wait a second, there are actually two conditions. I forgot about this one. The outliers condition. There are no outliers among the residuals, all right? That's a lot of conditions, but we need to check off all those boxes, or just about all of them, if we want to go on with the study and take our results with a grain of salt in order to do analysis, inference on beta 1. All right, so there is a process for performing inference with an ideal regression line. There is a process for this, okay? And it's because of kind of an awkward problem. We can't check some of the conditions for analyzing a regression model without first actually computing the regression model to find the residuals. That's a little awkward. It's like we have to confirm that we can do something by doing the thing. But here's how we get around this admittedly awkward problem. Here's the technique, if you will. We make a scatter plot to check for linearity, okay? If the data suggest a linear relationship, we need to find the regression line for the data to find the predicted y values and errors, all right? So we're going to find a regression line if we see a linear relationship. We're going to make a scatter plot of the residuals against x or against the predicted y values. You may recall on the prior slide the residuals plot at the bottom right was against predicted y values, not x values. Make sure the residuals lack an obvious pattern. We're going to make a histogram of the residuals to determine whether they're unimodal and symmetric. And then, and only then, should we proceed with inference. All right, we're going to do all of this with our study on the relationship between percent body fat and waist size in men. Right, so here is the scatter plot that we can fit a regression line to predict percent body fat given particular waist sizes, or can we? So we're going to see what conditions we can check off. Straight enough condition, yeah, the scatter plot seems to suggest a straight linear pattern. Independence assumption, all right, these data are not collected over time, and there's no reason to think that the percent body fat of one man influences the percent body fat of another. You can assume independence. But we do need to acknowledge that randomization is technically violated, and randomization is one of the ways we can really check that independence box, right? So randomization, these data are not from a random sample, but it's reasonable to assume these men are representative of the population. Then you have the random residuals condition. This residuals plot is a cloud of chaos, which is exactly what we want, all right? Does the plot thicken condition? The residuals shows no evidence of a change in the spread about the line. Again, it is a cloud of chaos. All right, so the residuals are random and there is no widening or narrowing that is clearly noticeable. We have the nearly normal condition and the outlier condition together. We have a histogram of the residuals is unimodal and symmetric and familiar, might I add, without outliers. Normal model is reasonable for the errors. All right, so all these residuals or errors, they do stack up to a bell-shaped looking histogram. So you really can't ask for anything better with real-world data. Under these conditions, a linear regression model is in fact appropriate. So here is an approximation of a regression line, and here are computer output related to that regression line. So the estimated regression line is the predicted percent body fat is equal to negative 42.73. How did we get that? We look at intercept and coefficient. There is my number for the intercept. And then we see plus 1.7 times the waist size. Where's the 1.7 coming from? We look at waist size, coefficient. There you go. There's the slope of the regression line. This is all taken from the data up here, specifically in the coefficient column. So we're able to pretty easily answer the question, what model best predicts body fat from waist size? And that would be this model right here. But now to our second question, how well does it do the job? We're going to look at a couple things. We're going to look at the R-squared value, that's the variation accounted for. We're also going to look at this standard error for the coefficient. This is not the standard error for the bivariate data as a whole. This is the standard error specifically for the coefficient, all right? This is a measure of, in repeated sampling, how variable is this coefficient going to be. Say we took a bunch of other samples of the same size, how variable is this coefficient going to be, this slope of our regression line? So, the R-squared for the regression line is about 67.8%. Waist size seems to account for about 2/3 of the percent body fat variation in men. All right, let's pause there for a second. R-squared is variation accounted for. That means that 67.8% of the variation in body fat percent is due to the variation of waist size. And the other part of 100%, I guess that would be 32.2% of the body fat percent variation may be due to other factors or is just due to chance. The slope of the line says that the percent body fat increases by about 1.7 percentage points for each additional inch of waist size on average, right? That's just a statement about the slope that's useful when we talk about the standard error of the slope, 0.07, and that is a significantly smaller number than the slope itself. Relative to this 1.7, 0.07 is a small number. It's not a lot of variation after repeated sampling. It looks like the estimate is reasonably precise, all right? If in reality the slope of the ideal regression line is different, it's not going to be that much different. Now we're going to talk about what makes for a good regression line. And just a heads up, this is going to get pretty technical, but we put it all together in a couple minutes. If we envision the regression line for a set of data to be like a sample mean, it's kind of like a measure of center in a one dimension, right? Rather than a single point, it's a line that's a measure of center. Then the residual standard deviation, labeled S sub e, is like a sample standard deviation of the data relative to the regression line, okay? And here is this formula, which should, if you have a good memory, look somewhat familiar. It looks a lot like the formula for standard deviation in one dimension, but now it's like we're doing standard deviation in two dimensions. This is the average sort of distance each point is from the regression line. And I say average because the square root makes things a little interesting, and that n minus 2 in the denominator, that's a long story as well. But it's more or less the average distance each point is from the regression line. With every regression line, we try to estimate beta naught and beta 1. But the smaller the residual standard deviation, the better we're going to be at guessing the betas. For example, our guesses for the betas are going to be more reliable given that top plot as opposed to the bottom plot. Because in this top plot right up here, we have a relatively, and relative to this messy plot down here, a small residual standard deviation. Are there residuals? Yeah. Are they huge? No. Down here, there are residuals, and they are quite large. Now we got to talk about these two plots right here. Which of these two scatter plots do you think would be better at predicting beta naught and beta 1? Well, if you tried to draw a regression line through this plot right here, how would it look? Would it look horizontal? Would it look almost vertical? It's hard to tell because this is just a blob of statistical chaos. This seems to follow a pattern. This plot right here would be better at predicting beta naught and beta 1. The second scatter plot is better at predicting the betas than the first. We see not only that the spread of the data about the regression model, but also the spread of the x values influences our ability to predict beta naught and beta 1. So a small residual standard deviation, like we saw in the last slide, is good, but what's also good is for data to be spread out x-wise. You'll notice that the x values of these points don't vary all that much. S sub x, the standard deviation of the x values of the points, is smaller here than it is here. These points are spread out for a wider range of the values of x. Or should I say, the standard deviation is greater. This plot will be better at predicting the betas. Now let's look at these two plots. Which plot do you think is going to be better at predicting the true regression line for the population? Well, I'm going to go with this one over here. The reason being, there are more points. The silver bullet in statistics is sample size, unless you sample more than 10% of the population, which most of the time is a big problem. Over here, we don't have as many data points. There does seem to be a general trend with a couple points bucking the trend down here, but there is a general trend, sure, but there aren't as many points. Here are a lot of points that seem to be all on the same track, as it were. Which of the two scatter plots is going to be better predicting the betas? I'm going with the one on the right. The second scatter plot is going to be better predicting the betas than the first. We also see sample size influences our ability to predict beta naught and beta 1. Now let's put it all together. We've seen that the residual standard deviation, S sub e, the spread of the x values of our points, S sub x, and n, our sample size, influence our ability to predict beta naught and beta 1, the population y-intercept and slope. We shouldn't be surprised that all three of these values affect the standard error of the slope of the regression line. So the standard error of b sub 1, which b sub 1 is what we use to predict beta 1, is influenced by all three of these variables that we have discussed. Knowing this, we are able to standardize the regression slopes and make a test statistic for performing inference. This, again, as I said, is very technical. Long story short, we are able to model the standard error or the variation of our predicted slopes of the regression line, the B1s that we would get from many samples. Say we took one sample, we would get a slope for that sample. Say we took another sample, we would get a slope for that second sample. Say we took many samples, we would get many, many slopes, all right? But what this is saying here is that those slopes are predictable, all right? They have a certain amount of variation. And when we can predict the variation of a value like B1, we are able to standardize the regression slopes, and that helps us to make a test statistic, which is our key to perform inference. Our test statistic is going to be B1 minus beta 1 over the standard error of B1. Well, what is beta 1 going to be in the null hypothesis? Well, in the null hypothesis, beta 1 is going to be 0. If we assume that there is no relationship between the variables, then beta 1 is going to be 0, right? If there is a relationship, then the ideal regression line is going to have a slope different than 0. So in our null hypothesis, we assume beta 1 equals 0, which means our test statistic just looks like this. We're going to use student's T model to analyze the slope of the regression line with n-2 degrees of freedom. We can also standardize the intercepts. We see that beta 1 is the star of the show and B1 is our predictor, our point estimate, we would say, for beta 1. The ones are the real stars here. We can do the same thing for the intercepts for beta naught using B naught, but there aren't really any applications we need to be concerned with. So we're just going to move on from here. Beta 1's the hero. Sorry, beta naught. So, now that we have a formula for the standard error of the slope and its sampling distribution, right? We'd use student's T, degrees of freedom n-2. We have a measure of spread for the slope. We have a sampling distribution. We have all the ingredients we need to perform inference. We can perform a t-test for the regression slope. We are able to perform inference at last. The hypotheses for a t-test for the regression slope are, as I've said before, h sub 0 is that beta 1 equals 0. The alternative hypothesis is that beta 1 does not equal 0. Either the slope is essentially nothing, or the slope is not nothing, and there's something interesting going on. We use these hypotheses because if the population features no meaningful relationship between the variables, the regression line has a slope of 0. For example, for these data right here, the regression line is going to have a slope of approximately 0 because this is a cloud of chaos. We can also compute a confidence interval for the regression slope, which is of this form. Our confidence interval would be our point estimate for beta 1, which is b1, the slope of our sample regression line, plus or minus a t-star value with n minus 2 degrees of freedom, times the standard error of b sub 1. So here we go. We are going to be interpreting a t-interval for the regression slope. The 95% confidence interval for beta 1 in the data relating waist size to percent body fat is this. All right? We have our point estimate, 1.7. That's the slope from our sample regression line, plus or minus a t-star value with 248 degrees of freedom. If you recall, our sample size was 250. We take away 2, so 248 degrees of freedom times the standard error for B1, which is 0.074. We're now going to practice finding this t-star value using inverse t. So let's get to work. We would go to second, distribution, and then number 4 is inverse t. Now for area, we need to remember that we're doing a 95% confidence interval, and inverse t starts accumulating area from the far left, all right? So we want a cutoff that would contain the 95% in the middle, as well as the 2.5% of the area under the curve to the left of the 95%. That's going to total to 0.975. The degrees of freedom, as we've said before, is 248. That's the sample size of 250 minus 2. We hit paste and enter. And that is our t-star value. So if we were to substitute that 1.97 approximately value in for our t-star, multiply that by 0.074, and then add and subtract that from 1.7, we would get our confidence interval for the slope. So this means that on average, there's an increase of between 1.55%, that would be 1.7 minus my t-star times 0.074, and 1.85%, that's 1.7 plus our t-star times 0.074, body fat per inch of waist size. Now that we've taken a peek at what a confidence interval looks like for the slope of the regression line, now we're going to perform inference ourselves. We're going to perform a t-test for the slope of the regression line, and we're going to close with a confidence interval, because why not? To the right are the times of the 11 top performers in women's marathons in the 1990s against the temperature during the race. Does the temperature have some kind of influence in the time it takes these women to complete the marathon? Our hypotheses are as follows. beta 1 equals 0 versus beta 1 does not equal 0. We need to check the conditions before we use LinRegTTest to compute the regression equation and confirm whether or not to reject the null hypothesis. We are going to state a conclusion using the context of the problem after that. And finally, to top it all off, we're going to be creating a 95% confidence interval for beta 1 and interpreting it in context. Here is a whole lot of calculator output that I produced on my digital graphing calculator, right? I'm going to leave a link in the description to a prior YouTube video in my AP Stat series to show you how to plot a scatter plot and to plot residuals in scatter plot form and in histogram form. But let's go through the conditions. The scatter plot shows a faint pattern, albeit with maybe one possible outlier over here, but there's generally an up and to the right sort of pattern. The sample is not random, so we cannot check off the box for randomization. We can check off the straight enough condition pretty easily, but the randomization condition is not there. These are the top 11 performers in the 1990s, so we'll need to be careful about how widely we apply these data. Looking at the residuals, there are no obvious patterns. That checks off the random residuals condition and the humorously named does the plot thicken condition. Can't really argue for either a pattern in the residuals or a thickening plot. The residuals are unimodal, and if you squint really hard, they are nearly symmetric too, without any real outliers to speak of. We don't have any boxes of our histogram floating out in oblivion, so we can conclude that the residuals are normal and that there are no big outliers. So we've checked off all the conditions. Let's get ready for some regression. So I've entered our bivariate data. Now I need to go to stat, I need to go to tests, and I need to go to LinRegTTest. Remember that old fella? So we have L1, L2, frequency, just leave that there. We need beta to not equal 0 for all our alternative hypothesis. We would say calculate from here, and we would get all the information we could possibly want. We get a p-value of approximately 0.285. We would get a value for A and B. Now, what's A and B? Well, A is what our textbook calls B sub 0, and B is what our textbook calls B sub 1. Okay? So, A and B are our estimates for beta naught and beta 1, respectively. So here's the resulting regression equation for our data, inputting A here and B here, that is B sub 0 here and B sub 1 here. We have the predicted time is equal to a function of the temperature. However, this regression line is not a terribly good predictive tool because of that p-value. The p-value of 0.285 is high. Therefore, I do not reject the null hypothesis. There is not sufficient evidence to confirm that there is an association between the temperature and the time to complete a marathon. Now let's find a confidence interval for beta 1 in LinRegTint. Same lists as before, 95% confidence, and here it is. So the 95% confidence interval for beta 1 is just what we got. We note a negative value on the left and a positive on the right. This means we can be 95% certain that on average there's an increase of between negative 0.032 and 0.097 minutes per degree, which is to say, since 0 is in the middle of this interval, There may not be an increase or decrease at all. It may just be a cloud of chaos. And here's your homework.